Hello, welcome to the HESA library, also called the HESA video bank. This is part 3 of a series of videos on biological chemistry. In this video, we'll talk about periodic properties, right? Yes, periodic properties. And so before we talk about periodic properties, we have to understand what periodic properties are. Then we'll talk about some terms that will affect periodic properties. Then we'll zoom into the periodic properties proper. So periodic property, we are saying they are physical and chemical properties of atom which recur on the periodic table. Physical and chemical properties of atom which reoccur on the periodic table. Examples are atomic ionic size, we'll talk about them. Ionization energy, we'll talk about it. Electron affinity and electronegativity, we'll talk about all of them. And some special terms for us to understand. For us to understand these terms, we have to look at the model of the atom like this. Now, usually what we draw first is the nucleus, and the nucleus is positively charged, right? Yes. Now, the force from the nucleus, the positive nucleus, is what we call the nuclear charge. The nuclear charge. The nuclear charge. Now, the electrons will be here. There will be 2 electrons here, and then there will be, let's say, if we are talking about, let's say, I've drawn 9 electrons. So 9. Let me add 1 to make it 10. Okay, let me maintain 9 so that we'll show the structure of fluorine. Right. Now, the electrons here, the ones in the inner shell here, are called the core electrons. They are called the core electrons. Core electrons. Okay, we have the term here. Now, the ones at the outermost shell, the electrons on the outermost shell are called the valence electron. Now, the important property, right? Because the valence electrons are the only electrons which are involved in chemical reaction. Now, all these properties, what we'll look at will be the attraction between the nuclear charge here and the valence electrons. Now, the truth is the electrons on the core electron, the electrons on the core shells here, the core electrons will reduce the extent of positivity that gets to the valence electrons. So, assuming the nuclear charge here coming is +10, right? +10 newtons. Now, by the time it gets to the valence electrons, it would get to, let's say, +8 newtons. That means the core electrons here have reduced the charge coming, right? So that's reduction is what we call the shielding effect. We call it the screening or the shielding effect done by the core electrons. Now, the net energy, the 8 newtons, which would be available to pull the electrons on the outermost shell or the valence shell, is called the effective nuclear charge. The effective nuclear charge. So these are the terminologies that we have to know. The positive center here is providing the nuclear charge. The electrons inside here are called core electrons. The electrons on the outermost shell are called valence electron. The electrons inside would provide something we call the screening effect, which will reduce the extent of positivity felt on the valence electrons. Very important to note. Right, so valence electron, outermost electron, they are involved in the bond. And that is what we look at. We look at the attraction between the positive nucleus and then the outermost electron. Core electrons are the inner electrons. They produce what we call the shielding effect or the screening effect. Now, effective nuclear charge will be the net attraction. Net because we have to subtract the screening effect from it, right? So the net or the effective attraction of the protons in the nucleus for the valence electrons, it increases across the period and decreases down the group. Now, the screening effect, it is the decreased attraction of protons for valence electrons by the core electrons. It increases down a group and decreases across the period. So the decrease in attraction. Right? Now, let's look at the trend that you have given us down the group and up across the period. So down the group, what happens is that more shells are added, right? More shells are added. So if you have something like hydrogen, which has 1 shell apart from the nucleus, 1 shell, it has just 1 shell. If you come down, you get lithium that has 2 shells. That has 2 shells. So more screening effects in lithium compared to hydrogen. Then When you come down, you get sodium. Sodium has 3 shells. So 1, 2, 3, right, with a nucleus in the middle like this. And so you realize that because more shells are added, the screening effect actually increases. It increases generally down. That's for the screening effect. Now, across the period, we don't add more shells, the same number of shells. So the screening effects remain the same. But what happens is that the atomic number increases across the period. The number of protons increases. If you move across the period, let's say from lithium to beryllium to boron, to beryllium to boron, right? What happens is that the number of shells don't increase, but the atomic number here is 3, the one here is 4, the one here is 5. So once we are increasing atomic number, what's happening is that the screening effect remains the same. So the screening effect does not really change, but the effective nuclear charge changes, right? Sorry, the nuclear charge changes because the number of protons increase. So it makes the effective nuclear charge increase across the period. So we are also explaining that increase across the period. Very important to note. Very important to note. Now, for effective nuclear charge down the period, even though the atomic number decreases down the period, we are saying that the increase in screening effect surpasses the increase in effective nuclear charge. So still you realize that the effective nuclear charge will decrease down the group. Very important to know. So that is how these ones will be. Now, the first property we have to talk about is the atomic radius. We have different ways of defining the atomic radius. One way has been shown here that if we have a molecule, like we have here, hydrogen gas, have the internuclear distance, have the distance between the nuclei, will be the atomic radius, right? Will be the atomic radius. Now, the size of the atom or the atomic radius is determined by how much the nucleus is pulling the outermost electrons, just the outermost, the valence electrons. How much the nucleus is pulling the outermost electron will show you the size of what? Of the atom, right? Now we are saying that across the period. Now across the period, because the shells don't increase, the same number of shells are there, but the protons or the atomic number increases, the size will decrease. The size will decrease. Down the group, because more shells are added, the screening effect is very great, right? And hence the atomic size increases. The atomic size increases. So these are the trends that we have to take note of when it comes, and the explanations are the ones that I have just mentioned. So the greater attraction of valence electrons, smaller size. So that is it. Now the note here says that when you are moving, you move from, let's say, lithium through to fluorine, right? Now the next from fluorine will be neon. Neon has a fully filled outermost shell. So because of the repulsion in the fully filled outermost shell, neon has a bigger size than fluorine. So when you're moving across the period, just as I've said, the size will decrease. But just between neon and fluorine, or between the noble gases and then the one that precedes them, the one that comes before them, right? You realize that there will be an abrupt increase in size because of what the repulsion in the fully filled shell for the rare or noble gases. So that's an exception for us to what? Take note of. Exception for us. So we said it reads that from the halogen to rare gases, there's an increase in the atomic size due to repulsion among the electrons in the outer shells. Very important to note. Now, cuts ionic radius. Now, what we have to know, the trend for what will happen along the period and down the group is the same. It's the same for cation and anion. But what we have to know is that for a cation, right, like sodium plus, compared to the parent sodium. Now, the meaning of this one is that it has lost, in the neutral atom, there are 11 protons and then 11 electrons, right? Yes, because it's neutral. Now, when it's plus one, it means it has lost 1 electron. So there will be 11 protons, but 10 electrons. Now, this case, we wanted 11 protons to pull 11 electrons. This case, we wanted 11 protons to pull what? 10 electrons. So we realized that the pull will be better when we have more of the protons pulling lesser of the electrons, right? And so we realized that for cations, the cationic size will always be smaller than the parent atomic size. And that is what we have to know at this point, right? Now, there's another term that we have to look at. That's isoelectronic species. Now, if we say something is isoelectronic, when we lose, like in this one, in this compound, the Na plus, when we lose one electron, the electrons left will become 10. Now, the 10 here is similar to neon, because neon has 10 electrons. 10 electrons. Now, this is also similar to fluorine minus, F minus, because F normally has 9 electrons, but when it's in a minus, it has added 1 electron to become what, 10, right? So when you have different species like this that have the same number of electrons, such that they will have the same number of, they will have the same electronic configuration, we call them isoelectronic species. So that is the term that has been put here. So we are saying that this one, the sodium here is isoelectronic 2. The neon here, the lithium here, when it loses the 1, is isoelectronic 2. The helium that we have there, very important to note. Let's move on. Now, for anion, let me do this direct narration. Fluorine has 9 electrons, 9 protons, and 9 electrons in the neutral state. When fluorine becomes F minus, it has 9 protons, but 10 electrons because it has gained an extra electron. Now, when you have 9 protons pulling 9, it's better than 9 protons pulling 10 electrons, right? So this size is not effectively pulled. So the anionic size are larger than the parent form, right? But all the trends will remain the same across the period and down the, so we don't have to worry about that. The next term they have introduced us is ionization energy. Now, the energy, the name gives it away because ionization, it means we are forming ion. The ion we are forming here, we are looking at forming positive ion. Now, how do we form positive ion? By losing electron, right? So the ionization is losing electron to form an ion. That's a positively charged ion. Now, the energy required to remove that electron is what we call the ionization energy. So we call the ionization energy. Now, take it from me. Every other property we'll talk about here is opposite to the atomic size. So I said atomic size, that's what? Atomic size. Atomic size across the group. When you look at the group, if you are moving across the group, right, the atomic size will decrease. Now, all the other properties, the ionization energy, the electronegativity, and then electron affinity will increase. They will act opposite, in the opposite direction to the atomic size. Now, I said down the period. Hey, sorry, I've mixed them. So, sorry. Across the period. So, across the period, what happens is the atomic size decreases. Across the period, atomic size decreases, right? Atomic size decreases. So what will happen to ionization, electron affinity, and then electronegativity is that it would increase. Now, down the group, what happens to atomic size is that it increases. It increases. What will happen to the other properties, the ionization energy, the electron affinity, and the electronegativity is that it would what? It would decrease. It would decrease. So that is that for that. Now, this will make you keeping the trend very easy for you. But let's come back to ionization energy. We have already defined ionization energy. Determinants of ionization energy is atomic size or atomic radius, which will be affected by the shielding and stability of the configuration. Now, this is very important. If you want to remove electron from a very stable species, like the noble gas, like neon, it is very difficult. So it gives very high energy, right? Yes, and then the penetrative power is the last factor. We are saying that down a group, the decrease in ionization energy. Reason is the increase in atomic size and screening effects, decreasing penetrative power. So the ability for you to remove electron. Now, when you have a bigger size, right, down the group, the size becomes bigger. When you have a bigger size, what happens is that the electrons in the outermost shell is less tightly pulled by the nucleus, so it is easier to remove. Right? As the size is increasing down the group, it's easier to remove. That's why the ionization energy decreases. But if you move across the period, the size is becoming smaller. it means that the outermost electrons are better pulled by the nucleus. And so it is very difficult for it to remove. So you need more energy to remove electrons. Right? That is what we talked about when it comes to that. But there are discrepancies. Let's talk about the discrepancies. Now, the discrepancies are best explained using stability. When you have a stable species, right, and you are removing electron, you require higher energy. And so between boron and then beryllium, right, boron has, beryllium has a higher energy, higher ionization energy because we are removing electron from 2s. Now the 2s here, what is peculiar about the 2s here is that it's fully filled. And fully filled is more stable than partially filled, right? If you look at the orbital box, this is fully filled. Now this one is the p. The p is partially filled, right? And so it is easier for you to remove it here. Even though boron has a smaller size, it is easier for you to remove it here than removing it from a fully filled s orbital here. So that is one discrepancy that we'll see. The other discrepancy would be between nitrogen and oxygen. Now, nitrogen has a half-filled. Nitrogen has a half-filled n orbital. Sorry, half-filled p orbital. 3 electrons, 1, 2, 3. Oxygen has a partially filled. 1, 2, 3, 4. And so it is easier for you to remove from a partially filled than a half-filled because half-filled orbitals are more stable than partially filled. In terms of stability, the fully filled is more stable, followed by half-filled, then partially filled comes. So you realize that the energy, the ionization energy for nitrogen is higher than that of oxygen, even though oxygen has a smaller size. That is because you are removing what electron from a half-filled orbital, which requires more energy because the half-filled orbital is what? It's more stable. Very important to note. Very important to note. Now we are saying to remove the second and third electron in the atom, the input of second and third ionization energy will be increasing. So what we are saying here is that sometimes for some of the compounds, like let's say oxygen can lose the first electron to form O minus, right? Oh no, I'm talking about positive charge. So if I'm using oxygen, I'll have to use plus. But let me find a more common metal to use. So let me use aluminium, right? Now, when aluminium is using the first electron, I'll form Al plus 1 electron, right? Now, when Al plus is losing 1 electron again, I'll form Al2 plus 1 electron, another electron. Now, Al2 plus can also lose electron to form Al3 plus, right? Plus an electron. Now, this is the first ionization. This is the second ionization, and this is the third ionization. We are saying that the first ionization sometimes is even positive. That means it releases electron to release energy. So this one is quite stable. But the second ionization energy, what happens here is that when we form the Al plus, now we have 13 protons pulling only 12 electrons, which is different from when we had the neutral atom when 13 protons were pulling 13 electrons. So because the pool is higher here, you require higher energy. Energy will be increasing. You require higher energy to what? To remove the next electron to form the Al2 plus. Now in the Al2 plus, Al3 plus, Al2 plus has 13 protons, but it has what? It has 11 electrons. So the pool is higher. So for you to remove 1 electron, for you to form Al3 plus, you have to what? Increase the energy. So you realize that the energy is increased for the second and third ionization energy. That is what that point means. Now the last point here says that where a noble gas electronic configuration is involved, an unusually high energy, ionization energy is required because of the stability. Now, noble gases are stable. So if you want to remove electron from a noble gas, it means you want to destroy the stability. And so you need a very high energy to do that. The next one here is electron affinity. Now, electron affinity, the name gives it away. It's how you can attract electron, right? How you love electron, how you can attract electron. So we are looking at how the atom can accept electron. Now the trend generally, I told you it is opposite that of the atomic size. So if the atomic size is decreasing across the period, electron affinity is increasing across the period. Down the group, atomic size increases, electron affinity decreases. Right, that is the general trend. Let's read what we have here. So we are seeing energy change when an electron is added to a gas, right? So examples have been illustrated here. Now, what is of importance to me is what's the behavior of oxygen. When oxygen is made to accept electron, the first electron, I get an energy which is negative. The energy which is negative means it is releasing the energy to the atmosphere, exothermic reaction, and hence there's high stability of even this one. But in the next instance, when I'm adding the next electron, I have to, the electron affinity is positive. Positive means I have to add extra energy, right? That's an endothermic reaction, And the idea is that in the neutral atom, oxygen, there are 8 protons attracting 8 electrons, right? Now, when you add 1 electron, as has been done here, it means now there will be 8 protons attracting 9 electrons. So, I mean, there's already expansion and repulsion, right? And then the nuclear charge cannot hold it effectively as it did in the oxygen. Now, for you to add an extra one, right? The electron that you added here has already increased repulsion in the outermost shell. So for you to add an extra one, you have to use a high energy to force the atom, the O minus, to accept it because of the repulsion that already exists, right? And that is why we have a high positive number, contrary to the negative number that implies stability in the first electron affinity. We are saying that down the group there's, okay, so I've explained all these. Electron affinity is clear with electronegative elements. So let's talk about the discrepancies. Unexpected lower negative electron affinity of fluorine. Now, fluorine, from the trend, right? Fluorine was supposed to have a high electron affinity, but fluorine has an issue with very small size. It has a very, very small size. Because of the size, the repulsion in fluorine is very strong, right? That has reduced the ability of fluorine to accept electrons. That is the electron affinity of fluorine. So that's something that we can take note of. Now, factors affecting electron affinity will be atomic radius, stability of the configuration, right? For a more stable configuration, if you're adding electron, it's very difficult, right? So it has a low electron affinity. Then charge carried. The charge carried, example will be the O and then the O minus that I showed, right? If it already has a negative charge and you want to add another electron, because of the high repulsion, right, you need very high energy to add. That means it will have a low electron affinity, right? So that's for that. Now, these are other discrepancies that we have observed. Boron. If you're adding electron to boron, you will get negative 27 degrees Celsius. Negative 27 kilojoule per mole. Now, if you are doing that to carbon, you get negative 122, right? Negative 122. And then if you are doing that to nitrogen, you get 0 kilojoule per mole. So now the significance of these figures are that if we have a higher negative, it means you are getting more stable product. That is more preferred. And that is more preferred. If you are getting a lower value, it means it's not very preferred. Now, the boron has a partially filled orbital. So adding 1 electron, it is easily accepted. You get a negative figure, fine. Now, for carbon also has a partially filled, but carbon's case, the reason why the negative is high, that's the negative is high means high stability, is because carbon has this. Carbon has, in the normal state without it accepting, it has 1, 2. Now, when you add this 1 electron, it becomes half filled. And I've told you that half filled is more stable. So because it will assume a half filled state, right? It will assume a half filled state. It gives what? A higher energy. It gives a higher energy. Now for nitrogen, you not get any energy because nitrogen already has a half filled state. So if you're adding electron, it means you are disrupting the stability. That is why you didn't get any high negative number. So that is the explanation for these discrepancies that we have seen in this particular one. Now, the next property that we have to talk about is electronegativity. Now, for electronegativity, we are looking at the behavior of atoms in a covalent bond. We have not discussed covalent bond yet, but covalent bond is a type of bond where there's sharing of electrons. So when two atoms are sharing electrons, one atom can pull the electrons more than the other. The ability to pull electrons in a bond that we are sharing is what we call electronegativity, right? It's the ability of an atom to attract the shared paired electrons to itself in a bond is what we call electronegativity. I've already explained the trend of electronegativity, right? I've explained the trend of electronegativity, so we don't have to worry ahead. Now, electronegativity has no units. You have to put that, keep that in mind. The highest value of electronegativity is 4.0, which is for fluorine. And then the lowest is 0.7, which is for francium, right? Now, most electronegative elements are reactive non-metal. So the halogens have the reputation of being highly electronegative. Let's keep this in mind. It will come in our discussion, right? The least electronegative elements are the group 1 elements, right? Very important. Now, let's talk about how bonds are formed. Now, the type of bond we are talking about is interatomic bonds. Interatomic bond. The first type that we have here is the ionic bond. The ionic bond. Now, the ionic bond is formed like this. If we have a metal like sodium, the sodium would lose the electron completely to form sodium metal, right? Sodium ion plus the electron. Now, if we have chlorine, right? Chlorine. Now, the chlorine can accept this electron, right, to become Cl minus. So, in the electrovalent bond, there's a complete transfer from the metal to the non-metal, complete transfer of electron, right? Now, when these ions will now attract electrostatic attraction, they are oppositely charged, plus minus, right? So there'll be attraction to form this bond. And that is what we call the ionic or the electrovalent bond, a very strong bond, right? Now, if you look at molecular bond, covalent bond, the next one. If you are looking at covalent bond, a covalent bond is sharing of electron, which is equally contributed by the species. And so you can have something like this, hydrogen. Now, hydrogen has one electron in the outermost shell. It has one electron, but it needs two to fill the shell. So what it can do is that it can overlap with another hydrogen, right? The hydrogen can overlap with that. And I said that this one will bring its electron, this one will bring its electron for them to share. Now, this is what we call covalent bond. This is what we call covalent bond. So this is covalent bond, right? Now, the last one is coordinate covalent bond. Coordinate covalent bond is also sharing, right? But in this particular sharing, one of the species will come with an empty orbital. So something like H plus. H plus has empty orbital. It has only one, normal hydrogen has only one electron. If it's H plus, it means it has lost the electron, so it has empty orbital. And then something like water. The oxygens in water have lone pairs. So the lone pair here, the two electrons can be contributed to the empty orbital to form H3O plus. This is how that compound is formed, coordinate covalent bond, H3O plus, right? Now, this type of sharing is an unequal sharing because it's formed from an unequal contribution because one of the species will bring two electrons and the other one will bring an empty orbital. It is different from the normal covalent bond when each of them will contribute an electron to be shared, right? So that is the explanation for that. Now let's read. We have explained the concept of ionic bonds, factors affecting ionic bonds. Now this illustration is the bond harbor cycle for sodium chloride, showing how the atoms would sequentially the process the atoms will go through before you can form your sodium chloride. So sodium solid would have to be vaporized by sublimation reaction. Now, after it being vaporized, it has to undergo ionization. And so that's ionization energy. And then for the chlorine, you have 2 molecules of chlorine already in the gas form. So you have to dissociate to get 1 mole of chlorine. And when we get 1 atom of chlorine, right? Then that chlorine has to accept the electrons coming from the sodium. So that's electron affinity, right? Then I'll get my Cl minus for them to now finally be an electrostatic attraction for me to form my sodium chloride. According to the Hess law, you can add all the energies. You can add all the energy of the individual step to produce what? To produce your enthalpy change for the reaction. Now, when the enthalpy change of formation is negative, negative means that you have released energy to the environment. It shows an exothermic reaction. You have released energy. Now, when you release energy into the environment, your internal energy becomes low. When your internal energy is low in chemistry, we say you are more stable. You are more stable. So that is what has been explained in blue, in yellow here. Very important. Now, the most important factor that affects the ionic bond first is low ionization energy. Now, the metal coming in should be able to easily donate the electron. That's the low ionization energy. High electron affinity. The non-metal should be able to easily accept that electron, right? And then the lattice energy will be the attraction between the positive and the negative charge. And then for good ionic compound, it should have a high lattice energy, high negative, right? Now, ionic bond formation is favored when the electronegativity difference is very high, right? Now, when the electronegativity difference between the atoms in play is greater than 1.7, then we are looking at that compound being an ionic compound. Very important. Now, when it's slightly less than 1.7, then we have a polar covalent compound. A covalent compound which is polar, right? And then if we have the difference in electronegativity very, very low, then we have a non-polar covalent compound. We'll talk about all these, the polar and non-polar covalent compound. So we have been given the electronegativities of atoms to find the nature of bonds that will be formed between them. So sodium and oxygen, the electronegativity difference will be 2.5, which is above 1.7, so it's ionic, most ionic compound. Then AlCl3, it is less than 1.7, so it's a polar covalent compound. Now the OF and the pH bonds are way lesser than very, very small. So those become non-polar compound. Now at this point, let me explain polar and non-polar compound. If we talk about covalent compound, right? Polar and non-polar covalent compounds fall under covalent compounds. So you still know that they are sharing of what? Electrons, right? Yes. Now, if I have something like H and Cl, the electronegativity difference between H and Cl is quite large. So what will happen here is that the electrons being shared here will be pulled towards the chlorine, said that the chlorine will have partial negative, and then the H will have a partial positive, right? This is what we call a polar covalent bond. If we say it's non-polar, non-polar is like we having two atoms of hydrogen, because they have the same electronegativity, the electrons are not really shifted towards each end, right? They are not really shifted towards each end. So that gives us what? A non-polar compound. There are no dipoles. So a polar compound will have dipoles, right? On them. Non-polar compounds will not have dipoles on them. Very important to note. Covalent bond. I've already explained covalent bond. What I didn't explain was the two types of bond that can form. Right? Now the two types will be the sigma bond and then the pi bond. The sigma bond. Now sigma bond is formed by a head-on overlap. A head-on overlap. So it can be between a p orbital. It can be between two p orbitals actually. It can be between a p orbital and another p orbital. Right? Like this head-on overlap. It can be between a p orbital and an s orbital. This is very common. This is very common. Or it can be between two s orbitals, right? Head-on overlap. So that will form a sigma bond, a very strong bond, stronger than the next one, which is the pi bond. Now, pi bond can only be formed between overlap of what? Of two p orbitals, two unhybridized p orbitals. Now, in this case, there will not be a head-on overlap as we have here, but there will be what? A side-by-side overlap. We call it a lateral overlap. A lateral overlap. That is what we'll have here. That is what we'll have here to form a pi bond. So pi bond is formed between two p orbitals, and it's what? It's a lateral overlap, side-by-side overlap, as compared to the head-on overlap in the sigma bond. Now, pi bonds are weaker and more reactive than sigma bonds. We have talked about that. Pi bonds are broken easily. Now, in between there are sigma bonds, only sigma bonds. Now, let me explain this. If you have every single bond, all the single bonds are sigma bonds, right? All single bonds are sigma bonds. But if I add one more, it means one of them is single and one of them is what? Pi bond. One of them is what? Sigma and one is pi bond. If I have a triple bond, it means one of them is sigma and two of them are what? Pi bonds, right? But every single bond is a sigma bond. Sigma bonds are more stable. They are the ones which are formed. And then the multiple bonds, the ones added are what? Are pi bonds. Very important. Very important. Hybridization. Now, before the overlaps can occur, what happens is that the orbitals are mixed. The atom makes their orbitals. Now, the reason why they mix their orbitals is that they want to form new orbitals which have lower energy and the same shape so that they can form the compound. They can use that to overlap and form the compound. I've already explained that lower energy means higher stability. And so hybridization occurs so that stability can be enhanced. Now, what is hybridization? It is the mixing of atomic orbitals of different shape and energy to form new orbitals of what? The same energy, shape, and direction. Right. Now, what we have to, or what is of importance to us here, or the most common atom that we meet when it comes to discussion about hybridization is what? Carbon. So they have drawn the carbon ground state to us, for us here. The ground state of carbon has been drawn for us here. Right. Now, before the ground state would react, it has to undergo what we call excitation. Excitation is a very simple process. What happens is that we promote one electron from the lower energy level to a higher energy level. So that's what has happened. We have removed this electron, then we have placed this electron here, right? So it gives us four orbitals, right? Four orbitals, this one, this one, this one, this one. Then we can mix them. Now it can mix all these four orbitals. When we mix all these four orbitals, that is one of the s orbitals and three of the p orbitals, we get sp3 hybridization. If we mix one of the s orbitals here and then two of the p orbitals, then we get sp2 hybridization. If we mix one orbital of the s and one of the p, then I get sp hybridization. So these are the three types of hybridization that we'll talk about here. Now, I cannot mix two of the p orbitals because the orbitals mixing in hybridization should be orbitals of different energy and shape. And if you are following our discussion, these are degenerate orbitals. They have the same energy. So we cannot mix the two of them. But we can mix the s orbital and the p orbital because they have different energy. They are not degenerate orbitals. So when we go down there, we see that hybridization, we have sp3 hybridization. That is when we mix the 1s and then the 3p orbitals, right? Now for that, we have four hybrid orbitals being produced. The bond angle between the orbitals will be 104, right? And the shape of the compound or the orbitals will be tetrahedral. There are some discrepancies that we have to take note of. In ammonia is sp3, the nitrogen ammonia is sp3, right? But because of the lone pair, this is, if I'm drawing ammonia, this is how I draw it. Because of the lone pairs of electron on the nitrogen here, it causes repulsion. And so it has reduced the bond angle from 109 to 107, right? And then the shape is also trigonal pyramidal. The shape will be trigonal pyramidal instead of the tetrahedral, right? So that is one of them. So that is what has been said down here. Let's move on. The anomaly is also seen in water. The oxygen in water is sp3, right? Water has 2 lone pairs, and so that gives a higher extent of repulsion than even in ammonia. And so you realize that the bond angle of water will further decrease to 104.5 degrees with a shape of being V or angular shape. Very important to note. Now, sp2 hybridization. sp2 hybridization. That's when we mix one s orbital and 2 p orbitals. We get orbitals with bond angle of 120. So the compound will have shape of 120 via sp2. And then the shape is trigonal shape, right? Now, when we use one of the S, let me go up and then show. If we have 3 at the excited state, we have 3 of the p orbitals always, right? Now, if we are talking about sp2, it means when we have one of the S forming the hybridization with 2 of the p, there's 1 p which is unhybridized, right? So that p would overlap with another p to form the pi bond. That appears to us as a double bond that we can see, right? That appears as a double bond that we can see. So that is where that double bond comes from. sp2 hybridization. Now the next one is sp hybridization, which involves only 2 orbitals with a bond angle of 180 degrees and a linear shape. An example is ethine, which has been given here. Right. Now these are representation of the hybridization, right? The shape of them. Let's take note of these shapes. The last type of bond that we have to, interatomic bond that we have to look at is dative covalent bond. I've explained that one of the species will bring an empty orbital and one of them will bring a lone pair, right? Oh, where does it go? So, yes. Now, species that can go through this type of reaction need a lone pair like we have here. Oxygen has a lone pair. The S2, S2 here, this one is filled, right? Nitrogen, oxygen has a lone pair. Nitrogen also has a lone pair, so they can undergo this type of reaction. So that's the example of compounds from this, right? Is these complexes are from there. Then we are saying hemoglobin has heme, which forms a dative covalent bond with nitrogen of some pyrroles. Some of these practical applications we have to keep. Now the octet rule. In compound formation, atoms transfer or share electrons to obtain a noble gas configuration. So we have been given sodium chloride. Now, when sodium loses 1 electron, it has 10 electrons now instead of 11. So it will assume the configuration of neon. When chlorine accepts 1 electron, it gets 18 instead of the 17. So it assumes a configuration of noble gas, which is what? Which is argon. So that's something that we have to look at. Now we are saying that the octet rule holds for some period 2 elements like carbon, nitrogen, oxygen, fluorine, but fails for other elements. Now the exception, always let's take note of the exception, PCl5. Now the PCl5 has expanded octet. PCl5, the P has more than just 8 electrons. The octet rule states that the maximum number of electrons the atom shell can take is 8, right? Yes, but the PCl5 here has more than 8 electrons in the outermost or the valence shell. So that is one deficient, that's one situation or scenario. Then we can also have a deficient octet, like the BF3 boron trifluoride. In boron trifluoride, the outermost electrons are 6 instead of the 8, right? So that's a scenario of what? Of a deficient octet. Now, bond versus lone pair repulsion. We have seen that repulsion in water and then ammonia. Now in water, we had 2 lone pairs, so the repulsion was higher. That is why we had a bond angle of 104.5, right? And so always it goes that lone pair to lone pair repulsion is greater than lone pair to bond pair repulsion. And the list of repulsions will be bond pair repulsion. That is what has been illustrated here, right? Now let's talk about bond angles. We are saying ionic compounds extend in all directions. So they are in all directions, right? And they are non-directional in that way. Now, covalent bonds are directional. Covalent bonds are directional. Any two covalent bonds separated by angles, right? Separated by angles. So if it's between sp3 hybridized, it's 109. If it's this is 18, right? 18. sp2 hybridized, that's 120 degrees. So that's the directional we are looking at, right? Now, in ammonia, it's expected to have tetrahedral shape, right? But because of the lone pair, the repulsion, it has 107 and it has a trigonal pyramidal shape. Water, because of the 2 lone pairs, right? So the lone pair repulsion is higher. It's high. So it will further decrease the angle to 104. 104, and the shape is being shaped. It's being shaped. Now we are saying water and ammonia are said to have distorted tetrahedron shape, right? Distorted tetrahedron shape. Now, let's introduce ourselves to the concept of polar and non-polar molecule. Polar and non-polar molecule. I've already talked about polar and non-polar molecules, right? That's a non-polar molecule comprised of similar atoms. That there's no tendency of one atom to attract the other, the shared pair of electrons towards themselves. So a hydrogen. Now, each hydrogen gas has 2 moles of 2 atoms of hydrogen. All the atoms are the same, so they can share the electrons equally. And that is what we call the non-polar covalent bond. Now, for the polar ones, they comprise of different atoms. So one atom has the tendency to attract the shared electron more than the other. Example is HCl. So HCl is a classical case of permanent dipole, polar molecules, right? Polar molecules. Now, the greater the electronegativity difference, the more polar the molecule is, right? Now, in terms of decreasing polarity, we have HF, HCl, HBr, and HI decreasing polarity. Let's take note of that arrangement. Now, sometimes there can be different polarities, right? Different atoms having different polarities, but because of arrangement, they can cancel out. So the example is carbon dioxide. Now, the whole molecule of carbon dioxide is non-polar. Even though each of the bonds here are polar, the bond here is polar. The carbon and the oxygen bond here is polar. The carbon and the oxygen bond here is polar. But because they are linearly shaped, now this side will cancel this side, and so the whole molecule becomes non-polar. Now, if you talk about the carbon tetrachloride, or the tetrachloromethane that we have here, we have this side is polar, this side is polar, this side is polar, this side is polar. But because of the even distribution, this side will cancel out this side, and then this side will cancel out this side for you to get a non-polar compound as a net. That is what happens. So sometimes the individual ones are polar, by net, because of cancellation, you can get what? A non-polar compound. A non-polar compound. Now, one characteristic of a polar compound is that it has dipole moment. It has permanent dipole moment. If we talk about dipole, we are talking about the charge multiplied by the distance from the center. Distance from the center. So if it's HCl as we have here, it will be the charge on the H, the partial positive multiplied by the distance, and then the chlorine 2 will have the same thing. Now, the higher the dipole moment, the higher the polarity, the more polar the compound is. The more polar the compound is. Now, we are saying that linear, trigonal, tetrahedral, and octahedral molecule have zero dipole moment due to symmetrical arrangement of bonds. I've already talked about that, right? So, example, the carbon tetrachloride that I use has what? Has tetrahedral shape. The carbon dioxide had linear shape, and you see that it didn't have any polarity because of the cancellation, because they cancel out. However, now these ones are not linear. H2, water is not linear, water is V-shaped. Ammonia is not trigonal. Ammonia is trigonal pyramidal, it's not trigonal planar, right? Now H2S2 is not linear, and so these two do not have a net of zero. They do not cancel out, they don't have a net of zero. There's a question here for us to try. Why does carbon dioxide and methane have zero dipoles? And they have zero dipoles because of their shape, right? Carbon dioxide is like this, right? There's polarity here, there's polarity here, but the dipole moments cancel out. Now for CH4, the same thing. There's polarity in all the bonds, but because of the even distribution, they cancel out. They cancel out. So that is that for. Now let's introduce ourselves to intermolecular forces. The first important thing that we have to look at is that the intermolecular forces will be responsible for the physical property and the physical state of molecules. The physical state of molecule will be as a result of what the intermolecular forces. And so the methane and then hydrogen sulfide is they are gases because of low intermolecular force. Water in chloroform is liquid because of high intermolecular force. Benzoic acid is solid because of higher intermolecular force. So that's what that's. Now, they also directly affect the physical property. So I've talked about that. Right. Now, there are types of intermolecular force. The first one is temporal induced dipole, temporary induced dipole. Induced dipole, induced dipole. We call it the weak van der Waals forces. Then we have permanent dipole, permanent dipole. So the induced dipole. Now, it happens between nonpolar compounds, compounds which are nonpolar, right? Now, there is an instantaneous polarity because electrons are not stable. Sorry, because electrons are not rigid, they are not stationary. That's the right way. Because electrons are not stationary, electrons being shared between, let's say, chlorine and chlorine, chlorine and chlorine. Now, these electrons are not stationary. So sometimes the electron can shift here. When they shift to this side, it gives this one partial negative, and this one will become partial positive. If I have another chlorine like this, right, and then there's disturbance for it to shift towards this side, I will get what? A partial negative and a partial positive at this side. Now, the attraction between these charges, right, the attraction between these charges is what results in what they induce dipole. And this is a very weak force, very, very, very weak force. So the instantaneous movement of the electron cloud, right? So cloud leads to this type of bond. So the attraction between these continuously changing instantaneous constitute the van der Waals attraction. Right now, the strength of the van der Waals forces or the induced dipole bond is influenced by molecular size. So the larger the molecular size, the more there are electrons and the higher the probability of distortion. And so the higher the force, right? The higher the force. And so if you look at this, now fluorine and chlorine are gases, right? Now when the molecular mass increases to bromine, it becomes liquid. Now bromine is liquid, even though the bond between it is van der Waals forces. It is liquid because it has high molecular weight. That will result in high van der Waals force. Now I2, which is for iodine crystal, is solid. It is solid. Even though the force is the same force, the same intermolecular force that exists between the fluorine gas, the same force that exists between what the iodine. But because the iodine has a higher molecular size, right, the force is stronger in the iodine, and hence it has resulted in what? In the iodine being solid, that is being crystals. So the induced dipole bond is favored by high molecular mass or high molecular size. Now the permanent dipole, right? There's a special type of permanent dipole which is called hydrogen bonding. Hydrogen bonding is formed by these three atoms and hydrogen, right? So nitrogen, oxygen, fluorine. Now these are the strongest of intermolecular forces that we know, right? For the covalent compound, these are one of the strongest that we can talk about. And so if we have this, usually they will have very high intermolecular forces. Right. Now, compounds that would exhibit the hydrogen bond would be ammonia. So that will take care of the nitrogen. Water, and then HF, hydrogen fluoride. These would have what that special type called the hydrogen bonding, which is stronger than the other types of permanent dipole. Now, the other ones, which are just normal permanent dipole, would be the example illustrated, the HCl. Now, in the HCl, there's permanent dipole, right? Because the chlorine is always more electronegative than the hydrogen. So there are permanent dipoles, and the attraction between the opposite charge induced dipoles, right? The opposite charge permanent dipoles is what keeps the molecules together. It's what keeps the molecules together. Very important for us to. Now let's look at this further. Clearly, the HF has the highest boiling point because it is would fall under the special type of hydrogen bond that is for special type of permanent dipole that is called the hydrogen bonding, right? Hydrogen bonding. That is why you see it having the highest energy there. Now there's a homework for us to try. They are asking us to explain how hydrogen bonding affects physical property of that's the boiling and melting point of HSN. Now, the boiling point of water is higher than H2S because water forms hydrogen bond, which is very strong compared to the H2S, which is permanent dipole bond. That is a simple answer for that question. Effect of hydrogen bond on solubility. For a solute to dissolve in a solvent, the attraction between the solid particles and the solvent particles should be greater than the attraction between the solid particles itself. Right? Very simple concepts for dissolution. Physical property of molecule depend on how many atoms are present. Now, we are saying that the higher the molecular mass, the greater the number of electrons per molecule, the greater the momentary polarization, then the greater the induced dipole. So this is giving us something about induced dipole. Now, as the number of carbons increase, our alkene passes from gases to liquids, then to solid. Right? This shows you that once you are adding more atoms or the molecular size is increasing, then you would have to proportionally increase the van der Waals forces between. Now, the last point, very important, effect of hydrogen. This is what relates to what we have to talk about. Now, their solubility in nonpolar solvent decreases because the increased number of bonds between the molecules needs more energy to be separated. The branch chain isomers of alkane have a smaller surface area for attachment and cannot fit so well in the liquid and solid. They have reduced van der Waals force. So now the last point here has introduced us to another concept. Van der Waals force is increased by higher molecular size as we have discussed, right? Higher molecular size as we have discussed. But another thing is that it's also increased by higher surface area. So when there's branching, when there's a branch chain, right, it reduces the surface area and what it will reduce the level of what van der Waals forces between them. The level of van der Waals forces between that molecule. So that is that for that. Now there are questions for us to try. The first one is why is water a liquid and H2S a gas? The water is a liquid because of a strong intermolecular force between it, which is the hydrogen bonding, right? The H2S undergoes permanent dipole bond, which is weaker. Now arrange the following substance in order of increasing boiling point, right? So the first one, increasing the lowest will be helium and then sodium helium and the bromine liquid have the same force. It has the same intermolecular force. That is, helium would be a gas. It would have weak van der Waals force. That's induced dipole. Bromine is also non-polar, right? So we would have induced dipole. That's the van der Waals force. But bromine has a higher molecular size, right, than helium, and so it would make it have a bigger boiling point. Then sodium chloride is an ionic compound. Usually interatomic bonds, all interatomic bonds are stronger than intermolecular bonds. So once we have a crystal like this, the ionic, the boiling point is very, very high. Now they are asking us to state all the type of bonding the atoms in this atom, ammonium chloride. Let me work on that quickly. Ammonium chloride. So this is the structure of ammonium chloride. So the bonds here are covalent bonds. These are all polar covalent bonds, right? The bonds here. Now, this arrow here shows dative covalent bond. It shows that the nitrogen here brought the lone pairs to this empty orbital of this hydrogen. So this is a dative covalent bond. And then between the N plus here and then the Cl minus here is ionic bond. So this one has ionic bond. This compound has ionic bond. That's between the N plus and then the Cl minus. It has dative covalent bond. That's between one of the hydrogens and the lone pairs on the nitrogen, right? It has dative covalent bond. And then it also has what? It also has normal polar covalent bond. It has normal covalent bond, polar covalent bond. Right. The last question says, which do you expect to form the strongest ionic bond? Now, what we use to determine the energy of the ionic bond is the lattice energy, right? The lattice energy. And the lattice energy is highly proportional to the charge, the product of the charge, Q1, Q2, right? But inversely proportional to the radius. Now, if you look at these two species, there's sodium, which has +1, chlorine has -1. There's sodium, which has +1, iodine -1. So the charges are the same. So what we can use are the sizes. And then the lattice energy is inversely proportional to what? To the sizes. Now, there are sodium in both cases, which are common, but chlorine and then iodine. Iodine has a larger size. And inverse proportionality means that once you have a larger size, you have a lower lattice energy. Once you have a lower lattice energy, you have a lower ionic bond strength. If you have a higher lattice energy, you have a higher ionic bond strength. So that is it, right? So this one that has a smaller size will have a higher ionic, a higher lattice energy, and therefore will have a higher ionic bond. Now, if I'm supposed to explain lattice energy as the last thing I will do here, lattice energy is the energy required to form 1 mole of an ionic compound from its gaseous constituent ions, or 1 mole, the energy required to break 1 mole of an ionic compound into its constituent ions. Right. So that is that for that. Now, if you have any question, kindly see any member of the HESA Academic Board. Thank you very much, and all the best in your exams.